7.6 Exponential growth and decay. When we're working with these growth and decays, you have a base and you have an exponent. That base is the constant, and the exponent is your independent variable. So with these functions, you have something that's called an asymptote. Just like what we did when we graphed those functions that we had a number to the power of x, you had an asymptote there. That just means that there's a certain point where that line does not cross over. So in some of these, you'll realize that that asymptote is the x-axis. So like if you look at this graph here that's graphed for you, that asymptote is the x-axis because it never crosses over that x-axis. Sometimes with these, you have an exponential growth and you have a decay. When you have these functions, they will look like x to a number to a power. When that power is your variable, that's when you have these functions. So if you look at the first set of examples, we're working with exponential functions that have numerical bases, and x is the independent variable as the exponent. So if you look at these examples, the first one we have is x to the third power. This here is not an exponential function because your variable is not the exponent. For the second one, you have 5 to the power of x. This one, yes, it is an exponential function because your variable, your variable, your x, is your exponent. Now, to figure out if you have a growth or decay, look at the number that the exponent is attached to. The x is attached to the 5 as its power. That 5 is a number that's greater than 1. So because the base is greater than 1, you have a growth. If you look at your third example, the negative 6 to the power of 2, that does not have an exponent. That's a variable, so that one is not an exponential function. Then your last one, you have 0.4 to the power of x. That one is, and then your numerical base is your 0.4. Because your base is less than 1, that one's a decay. So we look at our first examples that we are doing together. We have graphing numeric functions. So with these, I'll give you your x values, use your calculator, type in the function, and get your answer. So with the first one, we're telling whether it has a growth or decay, then we're graphing, and we're rounding all of our answers to the nearest tenth in order to graph. So if we look at this example, that 1.5 is a number that's greater than 1, so this is a growth. For our x values, we have negative 2, negative 1, 0, 1, and 2, and we're plugging that into the function f of x is equal to 1.5 to the power of x. If we do 1.5 to the power of negative 2, we're going to get 0.4 repeating. So this would be 1.5 to the power of negative 2, that's 0.4 repeating. So this is going to be negative 2, comma 0.4. For the negative 1, the 1.5 to the power of negative 1 gives us 0.6 repeating, so that's going to be negative 1, comma 0.7. For 0, any number raised to the power of 0 is 1, so that's going to be 0, 1. 1.5 to the power of 1 is 1.5, so that's the 1, 1.5. And then for 2, we're going to have 1.5 to the second power, which is 2.25, so that's going to round to 2.3. So 2, comma 2.3. To graph these, we're going to start at the negative 2, 0.4, which is going to be about here. Then we have negative 1, 0.7, 0, 1, 1.5, and then 2, 2.3. So this line is going to get really close to that x-axis. That x-axis is going to be your asymptote, and then that line goes up to the right. For your next example, you have g of x is equal to 30 times 0.8 to the power of x. Now, with this, you're looking at the number that has the x for the exponent. So that 0.8 is what you're going to use to tell if this is a growth or decay. 0.8 is less than 1, so this is a decay. If we plug in these x values, we have negative 5, 0, 5, 10, 15, and 20. So 30 times 0.8 to the power of negative 5 gives us 91 here. 30 times 0.8 to the power of negative 5 is going to give us 91.6. So this is negative 5, 91.6. For 0, we have 30 times 0.8 to the power of 0. So that's just 30 times 1, which is 30. So it's 0, 30. Then we have 5, so 30 to the times 0.8 to the 5th power. Now you can also do 0.8 to the 5th power, hit your enter button, and then multiply that by 30. That gives us 9.8. So that's 5, 9.8. For 10, we have 30 times 0.8 to the 10th power. So 0.8 to the 10th power, it's going to be 0.1, and if we multiply that by 30, we get 3.2. So that's 10, 3.2. For 15, we have 30 times 0.8 to the power of 15. So 0.8 to the power of 15 is 0.035. If we multiply that one by 30, we're going to get 1.1. So 15, 1.1. And then for 20, 30 times 0.8 to the power of 20 is going to give us 0.3. So it's 20, 0.3. So when we go to graph these, whatever we can graph, we will on this graph. So the only ones that we're going to really be able to graph is that 5, 9.8, 5, 9.8. And then we have 10, 3.2. 15, 1.1. So it's going to be about here, and then it's going to just keep going. So this we can graph, and it would look similar to this. With example C, we have 5 times 1.2 to the power of x. So that 1.2 tells us if we have a growth or decay. 1.2 is greater than 1, so we have a growth here. We have the function p of x is equal to 5 times 1.2 to the power of x. So we're going to do 5 times 1.2 to the power of negative 10. That's going to give us 0.8. So that's negative 10, 0.8. For the negative 5, 5 times 1.2 to the power of negative 5. Gives us 2.0, so that's negative 5, 2.0. For 0, that's 5 times 1.2 to the power of 0, which is 5 times 1, so that's just 5, so 0, 5. 5 times 1.2 to the power of 3 is 8.64, so that's going to be 3, 8.6. And then 5 to the times 1.2 to the power of 5. Is 12.4. So that's 5, 12.4. So to graph these, we're going to do the negative 10, 0.8 first. Then we have negative 5, 2, 0, 5, 3, 8, 6, 3, 8.6, and then 5, 12.4. So it's going to get really close to the x-axis and not intersect it, and then go up as it goes to the right. Our next part of our lesson deals with this formula, a of t is equal to a times 1 plus or minus r to the power of t. So this here can go ahead and deal with a growth or a decay, and it's just your initial amount is being multiplied by 1 plus or minus your rate of your increase or decrease to the power of the number of times or periods. So if we look at example A, it tells us that Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. Use a graph to find when the value of the guitar will be $60,000. So we don't have to use a graph with this, but we're going to use this formula to find between what 2 years it'll be at $60,000. So for this one, our rate is a increase, so we're going to use that plus. So we're going to use our initial amount, which was that $12,000. So A is 12,000. Our rate is 14%, which is 0.414. And then our period is what we're going to plug in for, okay? So our whole idea is to get our A of T equal to $60,000. Okay, so first we're going to plug this into our formula. A of T, so 60,000 is equal to our starting amount, which is 12,000, times 1 plus our rate, which is that 0.14 to the power of T. We want to find what that T is. So we're going to break this down even further to where it's 60,000 is equal to 12,000 times 1 plus 0.14 is 1.14 to the power of T. So with these, what I like to do is I like to start with 5. Plug the 5 in for T, see what you get. If I don't get a number that I'm looking for, I'm going to go up or I'm going to go down from there, depending on if I have an increase or a decrease. So the first one we're going to do, I'm going to try 5. So with 5, we have 12,000 times 1 plus 0.14 to the power of 5. If I work this out, this can actually be 1.14 to the power of 5. If I work this out, I get 23,104. That's not quite what I'm looking for. So I'm going to go up from here. Let's say I double the 5 and I work with 10. I plug the 10 in. I get 12,000 times 1.14 to the power of 10. This is going to give me 44,486. Still not quite where I want to be at. So if I look here, every 5 years, this is jumping about 20,000. So I'm going to try something like 12, because I don't want to go that far up. I want to be between 2 years that are between 60,000. So I'm going to try 12,000 times 1.14 to the power of 12 ends up giving me 57,814. That's closer, but I want to be at 60,000. That 60,000 is what I want. So I'm going to try 13. So 12,000 times 1.14 to the power of 13 gives me 65,908. So between these 2 years, it's going to be 60,000. So your answer with these is just going to be between what 2 years? So between 12 and 13 years, it'll be at worth 60,000. For B, we have in 1981, an Australian humpback whale population was 350 and has increased at a rate of about 14% each year since then. So that means that our starting amount, our initial amount, our A, is, we said 350. Our rate is the 14%, and it's an increase, so we're going to do 1 plus 0.14. We want to predict when our A of T will give us 20,000. So we're going to plug this into our formula. 20,000 is equal to to our starting amount of 350 times 1 plus our rate, since it's an increase, so that's 0.14 to the power of t. We're going to simplify this down even further. So 20,000 is equal to 350 times 1 plus the 0.14 is 1.14 to the power of t. So just with the last one, I'm going to start with 5. I'm going to have 350 times 1.14 to the 5th power. That gives me 673. That's not a big difference. So I'm going to jump a good amount here. Let's try 20. So if I jump 20, it's going to give me a 25. So that's going to be 350 times 1.14 to the power of 25. If I type this into my calculator and simplify, I get 9,261. Still not where I want to be. I want to be double that. So I'm going to try maybe 30. So let's try 30. So 350 times 1.14 to the 30th power. When I type this into my calculator, I get 17,832. So I'm going to try something closer to this, but not so far. So I want to try 31. So 350 times 1.14 to the 31st power gives me 20,329. So that is where that 20,000 lies between. So between 20 and 21 years is what my answer is. For C, we have the value of a truck bought new for 28,000. That's your A. Decreases, so this is going to be 1 minus our rate, by 9.5% each year. So our rate is 9.5, which is 0.095. Write an exponential function and graph. We're not graphing. Use a graph to predict, or use your numbers to predict when the value will fall to 5,000. So our A of t is 5,000. So we are going to have the formula here. 5,000 is equal to 28,000 times 1 minus our rate, which is 0.095. We're subtracting because we have a decrease to the power of t. So we're going to simplify this even further. So 5,000 is equal to 28,000. The 1 minus 0.95 is going to give us 0.905 to the power of t. So again, I'm going to start with, let's say, 5. If I plug the 5 in, 28,000 times 0.905 to the 5th power gives me 16,998. So that came down by about 8,000. So if I added another 10 to this, it should come down by another probably 8 or 9,000. So let's try 15. So 28,000 times 0.905 to the power of 15 is going to give me 6,264. So that's close. Try a number close to 15. I'm going to try 17. So 28,000 times 0.905 to the power of 17 gives me 5,130. So that's even closer to where I want to be. So I'm going to try 18 as well. So 28,000 times 0.905 to the power of 18 gives us 4643. So yes, that right there is where that 5,000 falls between. So between 17 and 18 years. For our last example, it says a motor scooter purchased for $1,000 depreciates, which just means there's a decrease. So we're going to start with our A of 1,000. We have a decrease of 15%. So our rate of 15% is 0.15 as a decimal, and we're decreasing, so that's going to be 1 minus our rate. And we want to know when it falls below. So our A of t is going to be 100. So this is going to give us 100 is equal to 1,000 times 1 minus 0.15 to the power of t. The 1 minus 0.15 is going to give us 0.85. So this is the same thing as 100 is equal to 1,000 times 0.85 to the power of t. So we're going to start with 5. For 5, 1,000 times 0.85 to the 5th power gives us 444. That number is not, we fall below, is not less than 100. So then try 10. 1,000 times 0.85 to the 10th power is going to give us 196. Your 196 is not less than 100, so that one doesn't work. If we try 15, we have 1,000 times 0.85 to the power of 15. That's going to give us 87. 87 is less than 100, but we want to make sure that that's the closest that it possibly can be. So let's just try the year before it, since we didn't have that one. So 1,000 times 0.85 to the 14th power is going to give us 102. 102 is not less than 100. And this here should have been less than, not greater than. Is not less than 100, but that 14, so that's not our answer. So after 15 years would be when it depreciates to below $100.